picking up where we left off, we have the derivative. It said find the points at which the graph of y equal x squared minus 3x has a horizontal tangent. The graph very, very, very roughly looked something like that. Very, very roughly. Not to scale at all. We said, 1, find f prime of x. We did that. F prime of x equals x squared minus 3. 2, set f prime of x equal to 0. No, that wasn't what f prime of x equals. Sorry about that. F prime of x was 2x minus 3. Then set f prime of x equal to 0. And 3, solve. And so without too much fuss, we get 2x equals 3, x equals 3 halves. Okay, almost there. So what we have there, x3 equals 3 halves, is the x coordinate where there is a horizontal tangent. That isn't quite what they asked for. They asked for x and y. So we need the corresponding y coordinate. Y coordinates always come from the original function. So if x equals 3 halves, y is going to be f of 3 halves, original function, 3 halves squared minus 3 times 3 halves, and we work that out. And so that's going to be 9/4 minus 9 halves, 9/4 minus 18/4, negative 9/4. And so finally, my answer to this problem is 3 halves, negative 9/4. And then you can check that by looking at a graph. And even my very rough graph doesn't look too far off. That could be x equals 3 halves. But if I look at my good graph, there's my good graph. And let's just go do a trace and go to 3 halves, which is 1.5. And it indeed does look where I would have a horizontal tangent. And it tells me that my y coordinate is negative 2.25, which is negative 9/4. So it absolutely checks. These problems, they're talking about graphical features, you can check by looking at a graph. Now these were relatively nice numbers, and so maybe you could have actually guessed from the graph. But if I'd made this a different problem where x equals square root of 2, you would have never guessed x equals square root of 2. So we still need the calculus to get those exact answers. But even if the answer had come out to be x equals square root of 2, you could look at the graph and estimate and see that your answer was reasonable. All these graphical things you can check by looking at a picture. And come test or quiz time, if you've got time at the end of the test or quiz, instead of getting up and leaving, check the things you can check. You might catch little tiny mistakes and fix them. And if you check something and it doesn't check and you can't find your mistake, you write me a note saying, I checked this, it's not right, can't find my mistake. And you will get more partial credit by telling me you know you're wrong than just hoping that I don't notice that you're wrong. So check these things that you can check. This one checks by looking at the picture and make sure that picture matches our calculations. Now globally, or what we're kind of alluding to here, is that when we find these horizontal tangents, and we'll be doing this a lot, you are predicting high and low points of the graph, what are called local or relative maxes and minimums. That's what the horizontal tangents are predicting for you. Okay, that's that problem. Okay, going on. So now we're just going to talk kind of more general about the derivative. So we have practiced finding the derivative using the definition, and the derivative is a limit. Limits don't always exist at certain points. And so that means the derivatives are not going to exist in certain cases. And so that's what we're going to discuss next, where derivatives do not exist. And we're going to discuss this point-wise. So kind of alluding here to what I already said, the derivative of a function with respect to x is the function f prime of x given by the limit as h goes 0, f of x plus h minus f of x all over h, provided the limit exists. Limits don't always exist. So there'll be times when the derivative doesn't exist, and we're going to investigate this graphically. We're not going to prove anything, you're just going to believe what I say here. We're going to investigate it graphically and find particular points where derivatives don't exist. So where derivatives do not exist. 1, at discontinuities. And we have the various reasons here, but here you have a removable discontinuity. And so there's x naught. Now if we go back to the point-wise definition of the derivative, the point-wise definition of the derivative has f prime of x naught in there. There's a missing point there. And so there is not a functional value here. So I can't say what f of x naught is, and if I can't say what f of x naught is, I can't do the derivative at that point. So derivatives do not exist at removable discontinuities. You don't have to remember the y, but there's the y. Infinite discontinuities, exact same thing here. There is not an x naught, or an f of x naught. There isn't a y coordinate there. F of x naught is my y coordinate. There's no y coordinate, so I can't do this definition. And then we have a jump discontinuity. Now, it's a little different reason here. It's not because I don't have a y coordinate. This guy has a y coordinate right there. The reason here is that if I think about slopes, the slope coming up on this side, remember limits have to be two-sided, so we're talking about slopes. And so doing the two-sided limit of that derivative limit which represents slope, if I think about the slopes, on this side the slope is positive, on this side it's negative. As I come towards that discontinuity, the slopes aren't going to match. I've got different slopes on the left and right. If left and right are different, there is no limit. Now again, you don't have to remember the y, but in this case it's about slopes. This is about missing y coordinates. Don't have to remember the y, but just remember derivatives do not exist at discontinuities. Next one, at corner points or cusps. So that's a corner point. There technically is a cusp. There is a technical definition of cusp. We won't go into that. So corner points or cusps, we'll think of the same thing. But again, it's about slopes. Slope on this side is negative. The slope on that side is positive. The slopes aren't matching up, so there can't be a derivative. And sort of the same thing here, slope negative, slope positive, slopes not matching up, and more precise, and so again, the slopes are not matching up, so there can't be a derivative. The slopes don't match up left and right. That means there's not going to be a left and right limit. The limits on left and right are going to be different, and so there's not going to be a derivative. But again, what you need to remember is that they're not derivatives at corner points and cusps. Then the last one that is much harder to see is this last one, vertical tangents. So I got a curve here, and right in the center of that curve, just for a instantaneous moment, that curve is perfectly vertical, just for that one point right there. And so if I'm going to draw a tangent line right at that one point, the tangent line has to be vertical. Vertical lines have undefined slopes. The derivative gives the slope. Well, if the slope is undefined and the derivative gives the slope, the derivative is undefined. So again, don't have to remember the y, but vertical tangents, or where you have a vertical tangent, is where the derivative doesn't exist because it's about the slope. At a vertical tangent, the slope would be undefined. If the slope is undefined, the derivative has to be undefined. So what you need to remember is derivatives don't exist at discontinuities, corner points and cusps, vertical tangents. Okay, we'll pause here and go to the next lecture.